In my Structural Engineering Made Simple series, today I would like to talk about reinforced concrete columns under biaxial bending moments, checking the design using Bresler's method. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Reinforced concrete columns are considered as slender members under an application of an axial load and two bending moments. The applied forces are an axial load, P sub u, a bending moment mxu about the xx axis of the cross section, and a bending moment fyu about the yy axis of the cross section. The xx axis constitutes the axis about which the major bending moment applies. Please notice that the subscript u indicates factor internal forces, which are sometimes also called design forces, and subscript n refers to nominal values of moment and axial load resistances. The applied internal forces are obtained based on structural analyses, applicable load combinations and load factors, and any adjustment because of the length effect. In this video, the procedure for checking a reinforced concrete section for the applied internal forces is presented. These are the notations. AST is a total cross-sectional area of steel. In the example shown, it is equal to AS plus A prime sub S. AS and A prime sub S are areas of steel on the tension and compression sides respectively. In the figure shown, compression steel and the compression side is to the right, tension steel and tension side is to the left. AG is the gross area of the section, B and H are cross-sectional dimensions, and D and D prime are distances showing locations of tension and compression bars. These are the pertinent references used for the preparation of this video. Procedure for checking column design. To check the design of a column for the biaxial moment effect, Bresler's method is used. This method was recommended in the ACI code prior to the 2014 edition. The current ACI provisions are more broad and do not outline any specific method for checking the design. Because of its simplicity, Bresler's method can still provide a convenient means for checking the design of a column. The method can be used as a quick and approximate process for a preliminary design or for verifying results from more detailed computer analyses for quality assurance purposes. Basic requirements. This method is used as a last step in verifying the design of a column. Therefore, we must make sure the following requirements are met through several prior calculation steps. The column cross-section, whether rectangular or circular, and the reinforcement arrangement are known. For example, as shown in this figure, a 16 by 16 inch cross-section is used with 8 number 9 longitudinal bars and number 4 ties at 1 foot 4 inches on centers. Steel and concrete material properties are known. All pertinent ACI requirements in terms of steel ratio, detail of steel, minimum protection cover, etc. have been checked and been satisfied. The applied axial load P sub u and moments mxu and myu have been computed based on the governing load combinations and load factors. Moments already include the column length effect and have been magnified accordingly. The interaction data for nominal load and bending moments for both the xx axis and yy axis of the cross-section have been determined. The applied axial load P sub u is larger than or equal to 0.15 Pn0, where Pn0 is the maximum nominal axial load resistance. In other words, when there are no moments applied. And phi is the resistance reduction factor, as explained later. For cases where P sub u is less than 0.15 Pn0, the axial load may be neglected. and the section is checked like a beam under a biaxial state of bending moment. Interaction data. The interaction data shows the combined effect of the axial load and bending moment in representing the resistance of the column cross-section. It is either shown graphically as presented below or in tabular forms. Notice that in these diagrams, the nominal values for axial load and bending moments are shown. These are the properties of the cross-section without being multiplied by the resistance reduction factor phi. The diagram to the left is the interaction diagram with respect to the major axis xx. The one to the right is with respect to the minor axis yy. Whether in graphics or tabular form, as indicated, the interaction data shows the combined effect of the axial load and bending moment in representing the resistance of the column cross-section. Notice that if there is no bending moment applied on the cross-section, the axial load resistance is maximum. With the application of the bending moment, the axial load resistance reduces. This is to say that in fact the cross-section has a limited capacity that must be shared between the axial load and bending moment. Each point on the interaction diagram represents one possible combination for the axial load and bending moment resistance among infinite possibilities. For example, in the figure shown, at point A, the resistance of the cross-section is PA, axial, and MA, moment. Notice that the eccentricity E is MA divided by PA. This eccentricity can be shown with the line drawn from the origin to the point A on the diagram with a slope 1 over E. You can use a number of sources available online to develop the interaction data for a given cross-section. Alternatively, you can use a CRST handbook or perform hand calculations using a few points along the diagram to make a table for Pn, Mn data. If you wish to develop the interaction data using hand calculations, use several strain diagrams across the cross-section of the column and complete a table representing Pn versus Mn and the eccentricity which is Mn over Pn. You can establish the strain diagram by selecting dimension x as shown below and also in the next slide. In this figure we show a strain diagram. The neutral axis is shown with the dimension x. The strain at the compressive fiber in concrete is 0.003, which is always the same value. The strain in the compression steel is epsilon prime sub s, and in the tension steel is epsilon s. This procedure is explained in the following slides for a simple case of one row of steel in each end of the cross-section without any intermediate rows of steel. For the simple case of one row of compression and one row of tension steel, the free body diagram for internal forces is shown here. The lower figure shows a free body diagram is a longitudinal detail of the column. And notice that the compression block on concrete is 0.85 prime sub c. The force in compression steel is A prime sub s F prime sub s, and the force in tension steel is AS Fs. We construct the strain diagram by selecting the dimension x, as we explained before, and write the equations for Pn and Mn based on the equilibrium. For the strain diagram shown, the corresponding Pn and Mn values represent, for example, the point D1 on the interaction curve of next slide. Please note that the configuration shown is for computing Mn with respect to x-axis. For y-axis, note that B becomes H and H becomes B. Also note that x-axis is along the centroid of the cross-section, thus dividing H into H over 2 and H over 2. And the centroid is different from the location of the neutral axis. We show a diagram here to the right, which is an alternate way of showing the interaction data. Notice that in this diagram, the resistance reduction factor phi has been applied. Furthermore, the ACI upper limits for the axial load has also been applied. The upper limit for the tight columns is 0.85 PN0 and for the spiral is 0.855 PN0. Also notice that the bottom portion of the curve has gone the other way and is sort of distorted. That's because the value of phi, the resistance reduction factor, eventually approaches to 0.9 for higher values of strain at the tension steel, as explained later. Again, notice that the left diagram uses Pn, Mn data, while the right one uses the resistance reduction factor. And recall that the subscript N refers to the nominal resistances. Please note that the strain diagram shown is only for one of infinite cases possible. To develop the interaction data, we will need the Pn and Mn for a handful of points. This can be achieved by selecting various strain diagrams, and for each strain diagram selected, we can find the forces and write two equations of equilibrium. The sum of forces will give us Pn, while the sum of moments with respect to the centroid will give us Mn. For each point marked on the interaction diagram, the strain diagram, the forces, and the equations for Pn and Mn are summarized in a table appearing later in this video. Pay attention to point C on the diagram. This is a special point. It corresponds to the balance condition. The balance condition is when the strain in the compressive fiber in concrete is 0.003, then the strain in the tension steel is exactly equal to the yield value. Also note that once the strain diagram is selected and X is known, we will have the following equations for other parameters needed for computing Pn and Mn. The dimension A is equal to beta 1x, where beta 1 is equal to 0.85 for a prime sub c less than or equal to 4000 psi. And a prime sub c is of course a compressive capacity of concrete. For compressive capacity above 4000, for every 1000 psi increase over 4000 psi, beta 1 is reduced by 0.05. The smallest possible value for beta 1 is 0.65. F prime sub s, which is a stress in the compression steel, is 87,000 times x minus d prime divided by x, and the absolute value of this stress cannot be larger than Fy. And the stress in tension steel is 87,000 times d minus x over x, and again the absolute value cannot exceed Fy. We are using pounds and inches in these equations. Generally, if a portion of the cross-section is under tension, the value of the stress Fs obtained from this equation will be positive. This is actually the tensile stress notation for this video. We use a positive value to show tension. However, if the value of Fs from this equation turns out to be negative, it means the distance x in the strain diagram is larger than d, and as such Fs is actually a compressive stress. Also note that similar to a beam design, the strain at the very first layer in the tension steel is epsilon t, which is 0.003 times dt minus x over x, and dt is equal to d in the example that we showed. This strain value is used in computing the resistance reduction factor phi. For tight columns, phi is equal to 0.65 when the strain is less than 0.002, and it is equal to 0.9 when epsilon t is larger than or equal to 0.005. For strain values between 0.002 and 0.005, we transition between 0.65 and 0.9 according to that middle equation. And if we have a spiral column, the lower value is 0.75, and the transition equation is the one shown below. Equations for hand calculations of various points along the interaction diagram, as shown in the figure below, are provided in the next slide. In the table provided in the following slides, the eccentricity and dimension x corresponding to the balance condition are shown with E sub b and x sub b respectively. X sub b corresponding to the balance condition can be obtained based on the equation 87,000 divided by 87,000 plus Fy, the quantity multiplied by dt, which approximately can be taken as 0.6 dt, again using pounds and inches as units. Here is the interaction diagram with several points on the graph shown. Notice that C is the balance condition. Points A, B1, B2, and B3 are in the upper portion of the curve, which is called the compression controlling area. And points D1, D2, D3 are in the lower portion of the curve, which are called the points on the tension controlling area of the curve. Here is a table showing the equations for f prime sub s, fs, pn, and mn for points A, B1, B2, B3, etc. Notice that at point C, fs is equal to Fy, and for all the values of x smaller than xb, the value of fs stays as Fy. And again, notice that fs is used positive when there is tension. Procedure for checking columns for axial bending moment using Bresler's equation. Bresler's equation uses the following equations for computing an equivalent axial load Pi. 1 over Pi is equal to 1 over Px plus 1 over Py minus 1 over Pn0. And as we explained before, Pn0 is the maximum nominal axial load capacity, which is 0.85 f prime sub c times Ag minus Ast plus Fi times Ast. P sub x is the axial load nominal capacity for an eccentricity Ey, which is equal to mxu divided by pu. In other words, Ex is 0. And Py is the axial load nominal capacity for an eccentricity Ex, which is myu divided by pu. In other words, Ey is equal to 0. The design is acceptable if the required axial capacity Pn, which is pu divided by phi, is less than or equal to Pi. The axial forces Px and Py can be obtained by using eccentricities Ey and Ex from the interaction diagram as shown below. For example, as shown in the left figure, we draw a line between the origin and the diagram using slope 1 over Ey. We draw a horizontal line going across and read Px. And then with respect to the minor axis, we use a slope of 1 over Ex, draw a horizontal line, and read Py. Alternatively, we can use Px and Py by interpolation using the table of values for Pn and Mn and E. In using Bresler's method, we can conservatively use phi is equal to 0.65 for tight columns and 0.75 for spiral columns. The example provided next is a tight column for which the capacity reduction factor phi is taken as 0.65. In this example, we consider a 16 by 16 inch column, that's a cross section with 8 number 9 bars. The values in the following tables represent the interaction data. Notice that the interaction diagram is identical with respect to the x-axis and the y-y axis of the cross section because of the symmetry. Furthermore, f prime sub c is 4,000 and Fy is 60,000 psi. The maximum axial load capacity is also computed, which is 1,323.2. The applied factor internal forces are computed and provided as follows. P sub u is 180 kips, MXU is 1,405 inch gips, and MYU is 702 inch gips. Therefore, the eccentricity EY, which is MXU divided by PU, is equal to 7.8 inches. By examining the interaction data, this value is between 7.33 and 10.13 inches. Therefore, Px is between 359.7 and 466.3 kips. By interpolation, we find Px as 448.4 kips. Now, similarly, Ex is equal to 702 divided by 180, which is 3.9 inches. And by interpolation between E equal to 3.7 and 4.52 inches, we can find out what Py is, which turns out to be equal to 721.5 kips. Therefore, 1 over Pi is 1 over 448.4 plus 1 over 721.5 minus 1 over 1323.2. Solving this equation would give us Pi equal to 349.6 kips. The required Pn is equal to Pu divided by 0.65, which is 180 divided by 0.65, which is 276.9. And since this is smaller than Pi, therefore our design is okay. The design provisions of ACI requires that the minimum bending moment considered, even though a structural analysis may show that either MXU or MYU or both are equal to 0. And as such, nearly all reinforced concrete columns will be under a state of biaxial bending moment, for which Bresler's method offers a convenient method for checking the design. Thank you for watching this video.